Hi everyone, welcome or welcome back to my channel. So in today's video we are going to solve a question that is based on binary search, and this is a really popular question. So the question is book allocation problem. So first let's see what question says. So we have been given an array of numbers, of integers basically, where each and every integer is going to represent the number of pages of the ith book. And we have been also given an integer m, which is going to represent the number of students. Okay. So we have to allocate all those books to the students so that each and every student should get at least one book. Okay. There should be no student who has got no books. And then each book should be allocated to only one student. Like no two students should get the same books, like that. And then the allocation should be contiguous. Then it's saying that allocate the books to those students in such a way that the maximum number of the pages assigned to a student is going to be minimized. Now, if you guys remember in the last lecture which I uploaded, we were solving aggressive cows problem. Okay. So there the scenario was just the opposite. There it was saying that the minimum number of, basically the minimum distance should be maximized. So I also told in that lecture that whenever the question is having this keyword, that something we are going to maximize, something we are going to minimize, there we can always apply binary search and answers. That logic. Okay. So let's see how we are going to solve it in this question. Now this is basically a pictorial representation that these are the books, let's say, and this is denoting the number of pages in each book and how we are going to denote it to the students. Now let's say we have a test case where there is an array with all these number of books. Now we have two students, m is 2, right? So in this example, basically I'm just telling you that how means in what way basically we are going to give the answer. Okay. So we have two students. Now we can have various permutations and combinations of rearrangement, right? That how we are going to distribute books to which student. There could be certain possibilities, and among that we have to see which is going to give the minimum maximum pages. That might sound confusing. I'm just explaining it at once. So suppose just notice the first row, this one, okay? Wait. Just try to notice this first row right now. Now we have this array. Now we are deciding, let's give the first book to the first student. Okay, so the first student got the book with 12 pages. So automatically the rest of the books will be allocated to the second student. Okay. Now with this arrangement, what we are noticing that the maximum number of books in this arrangement, basically the maximum number of pages in this arrangement has been given to the second student, that is the 191 is the total number of pages, right? Now we thought of the second arrangement, that let's give the first two books to the first student and the rest of the books to the another one. So in this arrangement we notice that to first student they are getting 46 pages in total, but the second student is getting total 157 pages. So in this possible arrangement, the maximum number of pages we are getting is 157. Then we notice the third possible arrangement, that let's give the first three books to the first student and the last book to the second one. Now in this we are noticing that the first student is getting 113 pages in total, but the second student is getting 90. So in total we can see that 113 pages are there in maximum. Now here what we have done, if you just see the question, what it is saying, in a way that the maximum number of pages assigned to each student. Now this is stating the maximum number of pages, okay, and we are going to minimize it because we have to minimize this maximum value. So if we try to minimize, we are going to get the answer 133 because this is the minimum one. Now how we are going to approach this question? I'm just taking this test case as an example right now. Now yesterday we solved a question of aggressive cows. So there basically our target was distance. Okay, we have to maximize or minimize whatever we had to play around. That was around distance. But here we have to play around the number of pages, right? So let's say, since we have to, it said that we have to basically minimize the maximum pages, right? So let us assume that we are targeting that at most 200 pages I can allot to the students. Now let's see if it is possible or not between these two students. So this is just a assumption which I'm making right now. Ki at most 200 pages I'll try to assign to each student at most. Just remember my words. At most 200 pages. It means if the number of pages is exceeding 200, so means then and there we are going to move to the next student. So let's start this thing. So first of all, we are going to start from the first student. We'll ask that can we allot the first book with 12 pages? It's less than 200, so we can allot it. Can we allot the book with 34 pages? Yes, it's less than 200, so we can allot it. Can we allot the book with 67 pages? Now, okay, so 67 plus 34 plus 12. The summation is going to be less than 200, so we can allot these pages to the first child. Okay, so the first student, yeah. Now then we are going to ask that can I allot the book with 90 pages to the first student? No. Here we can't do that because this summation is going to exceed 200. And our assumption was that we are going to allot the pages such that at most it can be 200. But if it's exceeding 200, we'll say that okay, I can't allot the book with 90 pages because capacity of student A has exceeded. So we're going to hand it over to the next student. So I'll give it to the student number 2. Okay. So what we can notice here that when we assume that maximum at most 200 pages we are going to allot, the arrangement is possible. We are able to distribute the books among the two students. Now it is saying to minimize it. Okay, we have to minimize the maximum number of pages. So if at 200 pages we are able to distribute it properly, then binary search will tell us that just try to shrink your space. Okay, so we are going to change the value from 200 to some lesser value. Let's say I'm just assuming right now because I'm not applying binary search in this assumption. So let us try for 150. It's less than 200. We are shrinking our capacity because if 200 is okay, for sure greater than 200 will work. So we are going to take the values lesser than 200. So let me try for 150. Again, I'll rewrite it once more. Okay. So again, we'll ask from student 1. Can we take the book with 12 pages? Yes, we can. Can we take the book with 34 pages? Yes, we can. Can we take the book with 67 pages? Let me count. 67. I think, yeah, we can take that. Okay, so it means it's allowed here, right? So we are going to shift this. Okay, now we are also going to ask that can we include this 90 pages book in that? So the thing is that if we are going to add this book with 90 pages, it is going to exceed the value of 150. So there we are going to say that we can hand it over to the next student because the capacity is exceeding. Okay. So here also we can see that with maximum capacity, if maximum capacity is 500, still we are able to rearrange the books among these two children. So again, the binary search will tell us that try to shrink your capacity. Okay, because our main goal is to minimize it, minimize the maximum number of pages. So let's say we are going to keep it at 120 or 100, let's say. Again, we're going to ask the same thing. Can we allot the book with 12 pages to the first student? Yes, we can. Can we allot the book with 34 pages to it? Yes, we can. Can we allot the book with 67 pages to it? Now, in this case, if we are going to allocate this book, then the summation is going to exceed 100 for sure. So that's why we are not going to do that. We'll move this book to the second child, second student, right? So similarly, I'm going to ask for the student also that can we. Okay, so then we are going to ask that is it possible to allot the next book with 67 pages to the second student? Then we can find out that yes, it's less than 100, so we can allot it to that. Now again we are going to ask that is adding the book with 90 pages possible here? Then we can see it's exceeding 100, so it's not possible in this case. For that we need to add one more extra student, right? But according to our given test case, we have only two students here. So if we need some extra student, it means with at most 100 pages, we can't distribute these particular books among two students. So binary search will say, okay, this is not under your capacity, you can increase it now. So again, we are going to take some value which is greater than 100, but that should be less than the previous value which we took, 150, I guess. Yeah, so this is how we are going to apply binary search. Why we are using binary search? Because we can see now if we are taking a particular range that let's say at most 100 we have taken. If 100 cannot satisfy the requirement of this question, the pages less than 100 could never do. Okay? If 150 could satisfy the condition, the page is greater than, that at most condition which we took, greater than 150 will always satisfy the condition. But since we have been told to basically minimize it, so that's why we are trying to find the optimal value. So this is how we are going to use binary search in this. Now let's go to the code and we'll try to understand that how we are implementing it. So first of all, we have been given this nums. Now one thing is clearly mentioned that each and every student should get at least one book. Now let's say the elements in the array, they are itself representing the books, right? Now let's say the array size is less than the number of students. That's not a possible case, okay? So in that case, we can return -1, okay? Let's say if nums.size, if it's less than k, let's say less than m here, then we can return -1, okay? Now, in binary search, we basically require some range. Okay. um, like what could be the minimum value? What could be the maximum value? Okay. So, if we take example of this test case, then what can be the maximum value? What can be the worst case scenario? You can say that we have only one student. Okay. Now, let's say if we have only one student, then what can we do is we can allocate the end. Sorry, we can allocate all the books to that one student. So that could be our maximum possible case. So we can write here I'll tell you about start also, but first let me write about end. So what we could do, we could basically allocate the entire pages, all the books to that one student. That could be our maximum, or you can say the worst case. So I'm using my accumulate function. Nums dot begin comma nums comma nums dot end starting from 0. Now, okay, so how we are going to initialize our start? Now, start is going to be basically the maximum element or the minimum element. Initially, when I thought that it could be the minimum one, but no, it will be the maximum element of all the array, means all among all the elements of the array. Now, why it's going to be the maximum element? Let's see. Now, if you guys remember the condition was that all the books should be allotted basically to the students, among the students. Okay. Now, let's say here, if we have taken instead of 100 pages, if somebody has assumed as 50 pages, then how can the student get the book with 90 pages? Because this is the utmost condition. So, we can't allot the book with 90 pages to the student. So we have to make sure that the start should always begin with the maximum element, that is the 90. Okay, so that's why we're going to write it's going to be the max uh, element of the entire array. Okay, so now let's start the binary search code. And one more modification, instead of int, I can take long. Okay, then I'm also initializing my answer as 0 or -1. I'm taking 0. Then while loop, mm, a minus s by 2. Now again we are using this formula instead of simply writing s plus e by 2, because that can break the code, or you can say that can basically increase the time complexity. Now this what we are doing, the assumptions which we made there now, that what number of pages we can take is at most. So that is basically going to be handled by this mid value. Okay. So again, the same thing which we are going to do. Now, here I'm going to write a function that will be basically performing all the logics which we did here. Okay. So right now I'm just keeping its name as isPossible. Now we'll also put certain parameters inside it. We'll see that later on. Now, if the particular combination is possible, what was binary search telling us? Since the question was telling us to minimize it, okay, binary search was telling us that okay, that's a possible answer. So you can keep it in your mind, or you can say you can store it somewhere. So I'm storing it in my answer variable, but it also told to explore, or you can say to shrink it, to shrink the search space. That okay, if suppose 150 is a possible answer, that's really good, but the value is greater than 150 will be the possible answers if 150 is okay. So it's better to shrink your search space and look for the values lesser than 150. So we are going to move our end to mid -1. Else, if suppose the arrangement was not possible with that mid value, so I'll be saying start is equals to mid plus 1. Then I'll be returning my answer. Okay. Now this function, this is possible what we are writing. This is going to be the main thing, this will contain the main logic. So let's try this. The parameters which I'm going to add here is nums. Then I'll be basically taking the mid variable int mid, and then int m, which is the number of students. Okay. Now what we were doing here, when I was asking it, key, can we allocate this book with 12 pages? Can we allocate this book with 34 pages? It was looking like, okay, we are adding it manually, but here also we are doing the same thing. Initially, we are going to allocate that, okay, let's say initially the pages are 0, and then we will be traversing. We'll be traversing throughout the array. Mm, is to 0, I less than nums dot size, I plus plus. And then we'll be checking one thing, that if pages plus nums I, what we were doing here, we were basically doing the cumulative addition, and we were checking that if the value is not exceeding this assumed value, we were checking this, right? And if it was exceeding, we were just adding on one more student, right? So we'll be checking that if pages plus numSci, if suppose this is going to be less than equals to mid, it means we can add it, we can continue adding it. Pages plus equals to numSci. And if it's not there, if it's exceeding that assumed value, then we can add one more student. Okay, now students are not initialized here. So student I'm going to initialize as 1, because by default we are taking one student initially and then we are performing the further operations. Students plus plus. Okay, and here I'll be doing one more thing. Okay, after adding students, we are going to reinitialize our pages with numSci. Why we are doing that? Because उसके पहले pages में जो भी value था that has been allocated to the previous student. From here, from the next student, we are doing the fresh start. Okay. Now after that, after when we are basically counting the number of students, if we are noticing that, let's say the number of students, if it has exceeded our total capacity, there was a case where we took the value as 100, I guess. Yeah, we took the value as 100 and we noticed that we required a third student, then that case was not possible. Okay. So here also, if we'll find out that number of students are coming out to be greater than m, then we can return false. It means this case is not possible. Okay, else we can return true. Then here also we should write the parameters. First was nums, second was mid, and third was m. Let me just read the code once. We wrote this condition at first, then we declared our start and then end. Then we declared a variable to store the answer. Then we are performing the binary search. Then we return the answer. Okay. Okay, it's all test cases are passing. Let me submit this. Okay, done. Talking about the space and time complexity, it's basically, since we're performing binary search, it's going to be bigger of login. But here also we are traversing throughout the array. So that's going to be bigger of n login. And for space, we're not taking any extra space as such. So that's going to be constant big of 1. So that was all about it. Thank you guys.